Okay. So part A is looking at the actual regression output now. So I'll make that a little easier to read. And so it's asking what the meaning of intercept beta naught and the slope beta 1 in this problem. And so our intercept is 0.47, and so that's basically saying that with no one in the arena, or in the arena, bets would be about $0.47 million, which doesn't make any sense. And that is because these data don't cover times when there's no one in the arena. And they don't cover times when more than, like, let's see, more than around, I think it was like 50,000 people are in the arena, or 55,000 is the highest. And so basically any data point, any value for x that you plug into the equation that isn't within the bounds of our data has a chance of not making any sense because we don't have data on those values. And so that's basically saying that, so beyond the scope of our data, the trend might not be linear. Because obviously if there's nobody there, bets are actually going to be zero. So the line might curve after that point. But for our data, we have a pretty linear relationship.
So when we're doing the homework or like on an exam, would he want us to say all of that? I mean, we'd explain the intercept, which totally makes sense, but then would he want us to go farther, or would you want us to go farther and say
you might want
it's
to
outside?
Say, like, this doesn't make sense because of such and such reason. Like,
okay.
Obviously, if there's no one in the arena, bets are going to be zero, not...
But you can just say it's outside the scope of our data?
Yeah. I mean, you don't have to have, like, a super long explanation about it or anything.
Thanks.
And so the B naught is always where it's like intercept correlation.
Yeah, it's where the line intercepts the y-axis. So yeah, it might. So usually the intercept doesn't make sense, and most people running regressions don't pay attention to it because most people don't have data when x is equal to 0, because it's not interesting to the question, basically. And it's easy to predict what happens when x is 0, kind of thing. But beta 1, on the other hand, is what we're interested in. And so basically what this number is telling us is that for every increase in attendance, so attendance is in thousands. So when attendance goes up by 1 unit, which would be by 1,000 people, our bets go up by $0.0146 million. And so that would be the average bet amount per 1,000 people, is what beta is telling us. So does that kind of make sense?
How do we know that is that where we're... Oh,
yeah, it's in the problem that attendance is 1,000 and bets are in millions.
That's B1.
Yes, this is B1.
That's the slope.
Yeah. So any questions about that? And so when you're asked about political significance or anything like that, so that is referring to the beta, to the slope. And so he can ask you about statistical significance with regressions or like political significance or like real world significance kind of a thing. And so that is basically saying if this number is relevant. And so if this number was really, really low, and it looks really low, but it's in terms of $1 million, and so it's actually a pretty significant number, then it matters. But if it was like basically 0, but still statistically significant, then you would say it's not politically significant or real world significant of a number. So real world significance is always referring to the beta coefficient. And you basically interpret the beta coefficient by saying by increasing p-value by a certain amount, you're talking about what impact that has on y. And so it would just be that number times y, or times whatever you're plugging in for x. So does that make sense? Okay. Okay, and so part B says, still interpreting beta 1, check if it is statistically significant. And so first it's asking what is its p-value. And so that's given to us right here. And so, can you guys all read this from your experience? Okay, so it's 3.9, and e to the negative of 0.7 means times 10 to the negative 7th power. So that's basically 0, because you move that over 7 decimal places. And so our p-value is basically 0, which basically says that at the 99.99999 confidence level, we can reject the null hypothesis. And so the null hypothesis in this case is exactly what part 2 of B is asking, that beta naught is equal to 0. And so we have our null hypothesis is that beta 1 equals 0, and our alternative hypothesis is that beta 1 does not equal 0. And so that's basically how we would find that, is by, it gives us the standard error and our coefficient. And so we would just plug in our actual coefficient, which is 0.0146, and then you minus what you're saying, what your hypothesis is, which is 0, and then you divide by the standard error, which is 0.0009. And so that number is given to us, so this is what t would equal. And we use the t distribution, not the z distribution, because we're using the standard error for the sample, not the standard error of the population. And so that's why we use the t distribution. And so our t is equal to 14.95 about, which if you remember at the 95% level, it's around 2 for the t statistic or z statistic that that you'll have basically that you'll have a significant beta. And so 14 is really big, which is why our p-value is very small. So if you...
Can you hit the light to the side chalkboard? Thank you.
Okay. So if you have, so this is basically saying at the 95% level, and we can look this up on the table to see what the actual number is on the t-table. I can find my t-table chart. Okay. So our degrees of freedom are n-1, so we have a sample of 10, so our degrees of freedom are 9, and then we're looking at at t equals 0.025 because you have 2.5% on each side. And so for this, our significant t is going to be 2.26. Negative 2.26. And so basically, our number is 14, which is going to be way out here. And so that's going to be in our reject the null hypothesis zone. And so this stuff should be familiar to you. But that's basically what the information in this output is looking at. We're given, you don't have to calculate it anymore, basically. We're given the standard error, you're given the t statistic, you're given the p-value, but that's just how you would interpret it. It's what we've been doing, like, the whole first half of the semester, is just calculating our T-score, which usually we've been doing it as a Z-score because we've had the population statistics instead of the population standard